Now let's look at two dependent samples, or as they are known as matched pairs. Now, this section will present methods for testing hypotheses and constructing confidence intervals involving the mean of the differences of the two values from two populations that are dependent in the sense that the data consists of matched pairs. For example, before and after measurements from the same subjects, or IQ scores, or husbands and wives. So that's what we mean by matched pairs. Now, the objectives, we're going to learn how to conduct the hypothesis test and use the difference from two dependent samples or matched pairs to test a claim about the mean of the population of all such differences. And then we are going to learn how to construct a confidence interval estimate of the mean of the population of all such differences. Now, this is the notation. D is the individual difference between the two values in a single matched pair. Mu D is the mean value of the differences D for the population of all matched pair of data. D bar is mean value of the difference D for the pair sample data. SD is the standard deviation of the differences D for the paired sample data, and N, number of pairs of sample data. Now, always check requirements. The sample data are dependent or matched pairs. The matched pairs are a simple random sample. Either or both of these conditions are satisfied. The number of pairs of sample data is large, more than 30, or the pairs of value have differences that are from a population having a distribution that is approximately normal. These methods are robust against departure from normality, so normality requirement is loose here. Now, this is the test statistic for dependent samples. And if we want to use p-values are provided automatically using technology, mainly a graphing calculator. And we are going to be using table A3 again for the student t distribution. And for table A3 t distribution, make sure we use n-1 degrees of freedom. And in order to construct the confidence interval, is going to be d bar plus or minus e. And this is the formula to find the margin of error. Now, first verify the sample data consists of dependent samples, and verify requirements are satisfied. Find the difference D for each pair of sample values. Find the value of D bar and S D bar. And for hypothesis test and confidence interval, use the t-test procedures used for a single population mean. Now, keep in mind that hypothesis tests and confidence intervals in this section use the same distribution as standard error, and they are equivalent in the sense that they result in the same conclusions. Consequently, no hypothesis that the mean difference equal to 0 can be tested by determining whether confidence interval includes 0. So let's look at an example. Are best actresses generally younger than best actors? Data lists ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. The ages are matched according to the year that the awards were presented. This is a small random selection of the available data so that we can better illustrate the procedures of this section. Use the sample data with the 0.05 significance level to test the claim that for the population of ages of best actresses and best actors, the difference have a mean less than 0. So what you're going to need to do is the years for actresses and actors are given. Now you need to find the difference between these two: 28 minus 62, 28 minus 37, 31 minus 36, 29 minus 38, 35 minus 29. Now, always check requirements. Samples are dependent because the values are matched by the year in which the words were given. The pair of data are randomly selected. Because the number of pair of data is 5, which is not large, we should check for normality of the difference and we should check for outliers. And there are no outliers, and normal contain plot should show that points approximate straight pattern. Unfortunately, it's not provided here. Now, the original claim is that the mean is less than 0. If the original claim is true, we have that mu d has to be greater than or equal to 0. Now, as usual, we need to identify the null hypothesis and the alternative hypothesis. The original claim is less than 0, so it becomes the alternative hypothesis, and the null hypothesis must be equal to 0. Significance level is 0.05. We already mentioned we need to use the t-distribution. Now we are going to need to figure out d bar, the mean difference between the two, and the standard deviation. And we get negative 10.2 years and 14.7 years respectively. Now, using these sample statistics and the assumption that the null hypothesis is equal to 0, we can now find the values of the test statistic. According to this is negative 1.557, about negative 1.56. And if you use technology, you get the same answer. Now, if we are going to use table A3, please take a moment and see if you agree with this value. So I'm going to stop for a moment. I'm going to let you check and see if you get this test statistic. Now let's look at this. Now we have degrees of freedom is 4, and now it's going to be 0.05 in one tail. So this should be the answer. But since it's to the left, it's going to be negative. But this is the answer, 2.132. So let's go back to the PowerPoint. So the test statistics is negative 1.557, which is this value. And we said that our critical value is negative 1.1. So what is going to be our conclusion? Because the test statistics falls in the non-critical region. Now, we are going to fail to reject the null hypothesis because the p-value is greater than the significance level. And if we use the critical value method, we also fail to reject because the test statistics doesn't fall in the critical region. So either one is equivalent. So we can conclude that there is no sufficient evidence to support that the mu d is less than 0. In other words, there is no sufficient evidence to support the claim that the population of ages of best actresses and best actors, the difference have a mean less than 0. Which means that there is no sufficient evidence to conclude that best actresses are generally younger than best actors. Now we're going to use the same sample data to construct a 90% confidence interval estimate of mu d. Now, keep in mind that alpha is 0.05, but 0.05 is only on one tail. Now, if you use technology, this is going to be given, okay? So according to this, the mu d is somewhere between negative 24.17 and 3.77. Now, this is the margin of error. So this is the formula. We're going to need to do d bar plus or minus e. And this is what you get, which is very close. Just look at these two numbers and look at these ones. So they are pretty close. So what is this telling us? So we are 90% confident that the limits between negative 24.2 years and 3.8 contain the true value of the mean of the age difference. That means in the long run, 90% of such samples will lead to confidence interval limit that actually do contain the true population mean of the difference. That means that this confidence interval does contain the value of 0. So it's possible that the mean of the difference is equal to 0 years, indicating that there is no significant difference between the ages of best actresses and best actors. We are not going to be looking at this method because it requires the bootstrap procedure, which requires technology. So with this, we conclude our module.